Hello, my name is Peter Lemaire, and I'm presenting my research on the solubility, viscosity, and cement absorption of solutions of C6F13 and C4F9 polyfluoroacrylates. Before we get into the methods and results of my experiment, I'm going to talk about how our group got interested in this and why it's an exciting topic of research. One of the unique properties of both liquid and supercritical CO2 is how low its viscosity is. It's about 10 times less viscous than water. However, in some applications that people want to use supercritical CO2, such as enhanced oil recovery, the viscosity is actually too low to be useful. The ideal recovery fluid has about the same viscosity as the oil it is replacing, but CO2's viscosity is about 10 times less viscous than that. In 1996, though, McLean and co-workers found that polyfluoroacrylates, shown on the right, could thicken CO2 substantially, so it became a much more interesting potential recovery additive. A few years later, Wang and co-workers created a copolymer with styrene, named PolyFast, that increased the thickening effect substantially, even to multiple hundreds of times at the optimal composition. Because of this, PFA and PolyFast solutions were tested for mobility control in sandstone cores. The initial tests were quite promising, getting up to 20 times viscosity increases in CO2. However, it was found that over longer times, PFA increased the pressure drop across the core greatly. Polymer had absorbed into the core walls, giving pressure drops 30 times higher than expected. This made mobility control unlikely to be viable, since we do not want to decrease the permeability of oil-producing formations. Then we thought, if it can decrease the permeability of a sandstone core, maybe we could use it to stop oil and natural gas from going where we don't want them to go. After some thinking and brainstorming, the idea of using PFA for wellbore integrity came to mind. It's such an important ecological and media topic, we were very excited to think that our polymer could make an impact on such an important field. Wellbore integrity, or the containment of production well fluids, is a huge media topic. Mostly every protest about wells stems from surface or subterranean contamination risks, so it is important to have robust solutions to address every problem and concern. There are many potential wellbore integrity problems, from the interlayer annular cracks such as 1 and 2, to translayer failures in 3 and 5, and cement defects like as seen in 4 and 6. Currently, there are a few methods for remediating failure at the wellbore. The first is cement pours, which are good for filling large voids in cement. It's cheap and bonds well with existing cement, but cannot be used if the failure cracks are small, or if it involves any of the metal casing. Epoxy resins can be engineered to work in a variety of environments and conditions and can fill some of the smaller cracks, as the resins can be made solids free, but their relatively high viscosities make it difficult for it to enter larger cracks. There are also some proprietary solutions, such as the seal-tight emulsion, which hardens and aggregates in the presence of large pressure drops, but it is unknown how much pressure drop is required to activate it and if it works in deeper wells. CO2 PFA solutions can add to the suite of wellbore integrity solutions by being able to seal the smallest of cracks and help seal off formations entirely. By being orders of magnitude less viscous than other liquid wellbore integrity solutions available totally solids free, it may be a good solution for sealing microfractures in wellbores where the other solutions cannot quite get to. So the question is, what exactly are these PFAs like? PFAs are stretchy, sticky, elastic polymers that don't dissolve in oil or water. They are stable in CO2 at wellbore conditions and soluble up to about 10% in carbon dioxide. Their C8 variant is the most thoroughly researched, but is restricted by the EPA, so we are focused on laying the groundwork for the C6 and C4 polymers, as they have been shown to have less of an environmental impact than the C8 type of polyfluoroacrylates. The idea is for the PFA CO2 solution to be injected into the well, which will seal off the opening sections of cracks wherever they may be. Then any additional PFA will permeate into the nearby formation and reduce its permeability, enhancing the seal for a retired formation. Initial tests were promising. When the PFA CO2 solution was flowed through a Portland cement core, over time, the pressure drop to keep a constant flow rate increased dramatically. After the test, we had to pry it apart and found that there was a white and yellow film on the cement, which was the PFA. An additional test was performed where we added a sand prop into the cement crack and flowed the PFA solution at a constant pressure drop. Over time, the flow rate reduced to 0. After the test, the polymer was holding the proppant in place, showing deposition had occurred again. However, C6 PFAs are not commonly studied in the literature, and their C4 counterparts are not present at all. Fluoropolymer companies transitioned to the C6-based polymers, but the only work in the literature on the exact polymer I'm using is by Zaberi and co-workers. So even though we have this good groundwork to work with, we need more quantitative information if we want to actually make this a useful product. We're also interested in C4F9 PFAs because there is some evidence that it is even better for the environment than C6F13 polymers. No research has been done on their properties, so we will have to answer whether these polymers retain the properties of C6 and C8-based PFAs ourselves. In our lab, we have a high temperature, high pressure, windowed variable volume, agitated invertible vessel that goes up to 180 degrees Celsius and 10,000 psi we call the Robinson cell. With it, we will take solubility and viscosity data, all while being able to see what is happening inside the cell. The solubility experiment is simple. I pressurize a CO2 PFA solution and mix until a single phase is formed. I then slowly expand it isothermally until the phases separate, as seen by the formation of a cloud in the clear single-phase solution. For viscosity, I use falling object viscometry, where I measure the velocity of a cylinder falling through the pressurized single-phase PFA CO2 mixture and compare it to pure CO2 under the same conditions to figure out the viscosity. We tested C6F13 solubility at 2 molecular weights, and as seen in previous experiments, the solubility is independent of concentration, but strongly dependent on temperature and weakly dependent on molecular weight. In the viscosity experiments, we also found the viscosity effects generally tended to increase with increasing PFA concentration and increasing pressure. Our initial tests on the C4F9-based PFAs were promising. Their solubilities in CO2 were comparable to that of the C6F13 polymers. We also found that the viscosity effects on CO2 were similar for the C6 and C4 polymers, making C4F9 PFAs a promising alternative to C6F13s as well. For additional characterization experiments, Dakin Industries in Japan and the National Energy Technology Lab down in Morgantown, West Virginia, are providing support for me with molecular weight and glass transition analysis and cement crack sealing experiments, respectively. At first, we wanted to use a CT scanner at NATL Morgantown to get crack sealing images, but ran into a few difficulties. At high pressures, the sleeve used to keep the cement stable in the CT scanner was eaten by the crack, damaging the sleeve and making the experiment impossible to complete. As a result, we went back to the experimental setup from the preliminary results I showed earlier. However, when we did the experiment this time, the cement was not sealed as expected. There was a slight pressure drop increase, but not nearly as dramatic of a sealing effect as we were expecting. Even still, we got some absorption of PFA onto the cement, as seen by the darker coloring of the cement in these pictures and its increased hydrophobicity. You can see by the fact that a water droplet on the darker part beat it up, while on the lighter part it spread out, giving us an indication that PFA was present on the darker surfaces. Unfortunately, though, these tests led to significant PFA contamination of the equipment at NETL, so we will have to try other methods for future tests. Our next attempt then will be for NETL to supply us with cylinders that we will put in the Robinson cell with a solution of pressurized CO2 and PFA. We will then let it sit for 24 hours so that the PFA absorb in the crack and return it to NETL Morgantown for CT and permeability measurements. Future experiments include determining PFA absorption on cement more quantitatively, characterizing more PFA samples with Dakin Industries, and continuing the cement sealing work with NETL Morgantown. I'd like to thank my advisor, Professor Robert Enoch, for all his support, Dr. Gianfranco Rodriguez for training me on the Robinson cell, Sarah, Professor Alenzi, and Parth for helping me with various stages of my research, and Professors Morsi, Bunger, and Beckman for helpful conversations and advice. From NETL Morgantown, I would like to thank Drs. Dustin Crandall and Barbara Kuchko for making this collaboration happen, and to Drs. Frank Adamski and Shinsuke Oshita at Dakin Industries for their support in polymer characterization. Thank you for your time, and I hope you enjoyed the presentation.